Okay, good morning, everyone. Welcome to the final webinar in our fall webinar series on insects and wildfire. My name is Carrie Berger, and I'm part of the Northwest Fire Science Consortium team, and I'll be the moderator today. If you have a question or a comment, please type those in the chat box, and Dave and/or Michelle will get to your questions towards the end of their presentation. So I'll record the webinar and post it along with our other webinars to our website, and the link to that website can be found under the notes box. So, okay, thanks for tuning in today. I'd like to introduce Dr. Dave Shaw and Michelle Agne from the College of Forestry at Oregon State University. And so Dave and Michelle, whenever you're ready.
Hello, everybody. This is Dave Shaw. Michelle will jump in here in about 20 minutes or so. We're pretty excited about making this presentation. There's some really interesting. We did a joint fire science project, and then a fire came along, and we have, I think, a pretty interesting story to tell. It's fairly unique to the climax lodgepole pine forest of South Central Oregon. Um, The presentation overview, it's going to be a focus on a brief review of mountain pine beetle and fuels in our region and reporting from a joint fire science project that we completed a few years ago. And then Michelle is going to follow up with her assessment of the Pole Creek fire and research team. Travis Woolley was very instrumental in a lot of this work. Our research team on the mountain pine beetle and fire and fuels was a fairly big group from Oregon State. We had help from the Llewellyn Hollingsworth and Laurie Kurth were involved from the Missoula Fire Lab, Jane Smith from the PNW Research Station, and Andy Iglesias from Forest Health Protection. This project would not be possible without aerial detection survey. The data on the time of outbreak and where the outbreaks occurred all came from aerial survey. So we really want to give aerial survey a shout out here and the importance of the data that they collect. For example, here's a map of bark beetles outbreaks in the West that Ken Rafa and colleagues put together in 2008 in a bioscience article. You can see mountain pine beetle in red, spruce beetle in green, and pinyon nips in blue. So it's very extensive, and this extensive mortality has brought up a lot of questions regarding fire and fuels and how the beetles are interacting and what the implications are. The area we're focused on here in the red circle is the South Central Oregon, and you can see there's been some pretty major mortality here. In the recent years, this is recent mountain pine beetle activity in Oregon from 2002 forward. And you can see this area here in the, there's this large sort of opening here, and this is where much of the beetle occurred in the 80s. The area we're talking about is here in South Central Oregon on the east slope of the Cascades on the Deschutes and Fremont National Forests. Mountain pine beetle has been particularly active in this region, but it's been ongoing since we've been following it since 1980. The 80s was when things really peaked in Oregon and in the South Central Oregon area. The outbreak in the region peaked at over 1 million acres locally and almost 2 million acres throughout Oregon. Then the epidemic quieted down a little bit, but continued. There was a lull right through the 2000, and then we really saw an uptick in 2006 to 2010, and that's what brought a lot of concern up, and that's when much of the West suffered the beetle activity. Just to review, the lodgepole pine forests in Central Oregon or South Central Oregon are fairly unique. This graph in the upper right shows the distribution of climax ponderosa pine and climax Pinus contorta. And you can see the climax Pinus contorta is restricted to the South Central Oregon region. And in the lower right, we have distribution of the habitat through the range. These are really fascinating forests. Some of them are fairly low elevation for lodgepole pine. They're topographic climax. There's low or no cone serotiny, and these tend to be single species stands that interact with fire, mountain pine beetle, and also dwarf mistletoe and root and butt rods. A fairly unique region and of lodgepole pine. The fire regime here is very mixed. There's low, moderate, and severe stand replacement fires in the region. The average fire return interval is probably in the range of 60 to 80 years, but there's a lot of variation. And some recent studies have suggested 20 to 80 years, and other studies 60 to 300 years. So there's a lot of variation on the landscape due to the complexity, even though it's primarily single species stands. The vegetation type here is highly variable. It's very typical though that it's sparse. The canopy is also fairly sparse, really low bulk density, canopy bulk density, widely distributed trees, lots of bare ground, and discontinuous surface fuels. So this topographic climax is one of the more low productivity forests in Oregon, but it's very unique in its structure. The mountain pine beetle has a major influence on the structure of these stands. The dominant paradigm is that in the endemic phase, when the beetle is not in outbreak, they're focusing on low vigor and damaged trees to survive in the region. When they move into an epidemic phase, the beetles focus on the dominant and the codominant trees, as in this picture here. You can see that it's basically the outbreak rolled through here and it's removing the dominant codominant trees until these trees are really exhausted. And then as the beetles move into the suppressed and intermediate trees and mistletoe infected trees, their fecundity really craters and the epidemic collapses locally. As you can see from this picture at Campbell Lake on the Fremont, where they've done some hazard tree reduction around the recreation area, the beetle removes these dominant and codominant trees and leaves these intermediate and suppressed. And you can see there's still a lot of green trees in this system, but as I said, the dominant and the codominants are the ones that are being removed. So these outbreaks don't happen in 1 or 2 years. They can last up to a decade or more in an individual stand, slowly taking out the dominant codominant cohort. But with time, essentially, you have this red phase. This is from all the knowledge we have with mountain pine beetle. Then it moves in, after the needles are lost from these trees, it moves into a gray phase with twigs, and then gray phase with larger branches, and then snagfall begins. You get understory redevelopment and forest canopy recovery after many decades. Again, in the Central Oregon Climax Lodgepole Pine Forest, this is unique because these are single species stand. In this photo on the right, you can see what we're talking about. The regeneration is all lodgepole pine. The intermediate classes are all lodgepole pine. There's dwarf mistletoe in this stand. The canopy bulk density is pretty low. There's not a lot of connectivity, and there isn't a lot of associated vegetation on the forest floor. This is another view of the Fremont Wainema area with the gray stage. So area detection survey provided this data. The green is in the late 70s through the 80s. And then as we approach recent time, it gets yellow and red. And you can see the distribution across the Deschutes and Fremont Wainema in the lodgepole pine type here. Has pretty much all been hit by mountain pine beetle. Our, we designed a really interesting plot approach. We took a chronosequence from 78 to 2010, and we attempted to get a replication across various years during the outbreak. We were able to find 19 distinct years where there was enough spatial extent that we could try to get about 12 plots in at each year. And we were able to get about 213 randomly located plots across the distribution of the lodgepole pine. So we feel like this is a very robust study with a lot of inference for the local lodgepole pine type. We divided this basically into four stages. Our time sense beetle one is lasted about 2 to 4 years after the mountain pine beetle moved into the stands. There was very little influence on surface fuels, but a lot of influence on canopy fuels in this stage. But you can see there's still red. Um, there's dead trees in the canopy, but the understory is still alive in this top left photo here. Moving into time sense beetle 2, we grouped these into 5 to 13 years. And you can see there's beginning of some surface fuels, but it's really the canopy that is profoundly influenced. And then snags, the snags that were created in time sense beetle 1 at the time of the epidemic then begin to fall at the end of this. So this is really the beginning of the snag fall phase. And then in time sense beetle 3, about 14 to 25 years post mountain pine beetle, you can see there's the snagfall is ongoing and usually is completely over by 25 years or so from the main pulse of the mountain pine beetle. The canopy is really open, and there's a lot of regeneration that begins, and you can see some of these dwarf mistletoe brooms also persisting in these stands. And then time since beetle 4, about 26 years to 32 years in our study, the canopy is recovering from its pre-beetle epidemic, and we're starting to get a lot of regeneration, and there's a lot of coarse fuels on the forest floor. So I have a series of graphs now that sort of represent this in canopy fuels and surface fuels. In this particular figure, we've divided the stages into the four stages, with red being the red phase, gray being essentially the gray phase, and then time since beetle 3 and 4 being the post snagfall and canopy and crown recovery. Live basal area is pretty obvious. You get some mortality, but you don't kill everything. If you can see in the dead basal area, it's really significantly standing dead basal area in the canopy is in time sense 1 and 2, and then all the snags pretty much fall down in time sense beetle 3. Canopy height recovers. Overstory canopy closure is probably one of the more important attributes that really changes and densifies in time sense beetle 3 and 4. Canopy bulk density recovers, and canopy base height is variable throughout the development post mountain pine beetle mortality. This figure is a representation of some of that same data, but it's with each year is represented by 12 plots. So there's 19 dots across the framework due to the 19 years we were able to sample. And you can see a little bit more of the subtlety and a lot of the variation. There was a lot of variability in some of these ages, but canopy base height seems to have dropped and then gone up, but the averages are more similar. Um, Canopy bulk density definitely was one of the strong, and overstory canopy closure were all very strongly influenced by time sense beetle. In terms of the surface fuels, these are the patterns we saw associated with each of the stages that we went through. The 1 hour fuels changed a little, they peaked, but the 10-hour fuels also, it's really the time between TSB2 and TSB3 when we see a lot of significant changes in 100-hour fuels and 1,000-hour fuels. But the litter biomass, the duff biomass, didn't really change significantly. So these are sort of nuanced stands compared to other lodgepole pine forests. Here again is the each year represented by a dot to give you a little bit more insight into these patterns and some of the variability that occurred. Um, Really, the 100-hour fuels really seem to change with time-sense beetle 2 to 3, and 1,000-hour fuels also changed. We're not 100% sure what's going on with the 1,000-hour fuels in time-sense beetle 32 years or so. Although there is a strong drop off there, we don't think that's a decomposition thing. We think that may be more associated with the intensity of the beetle epidemics in the uh, 79 to 80 rather than an actual pattern. So one of the other things I wanted to mention is that lodgepole pine dwarf mistletoe also plays an important role and interacts with mountain pine beetle and fire in terms of the structuring these ecosystems. We found it on over 70% of our plots, and on some of the plots it was very heavy. So Michelle Agne did a master's thesis on this, and you can see in this picture on the left, there's this tree here is a shrub created by dwarf mistletoe. These trees in the background have heavy brooms from dwarf mistletoe. In the panels on the right, figure A, there's no dwarf mistletoe in that stand, whereas in panel B, there's abundant dwarf mistletoe. So you can see that dwarf mistletoe has an influence on the forest structure also, and it's going to interact with mountain pine beetle and fire. So here's a fire that burned on the Deschutes and then slowly went out right at the margin here. You can see this is still a red phase mountain pine beetle time, so the fire didn't actually take off. So the discontinuous fuels have some influence on this. So in south central Oregon, the lodgepole pine forests are just a unique type of forest. These are topographic climax forests, single species, typically mixed age stands. Sometimes you can find cohorts of even age stand, but in general, it's a mixed aged environment, low canopy bulk density, low herbaceous fuels, and discontinuous fuels. In general, they follow the patterns that have already been known for mountain pine beetle outbreaks, where there's mortality in the dominant and codominant overstory of your lodgepole pine. Canopy bulk density is significantly reduced and then recovers, and snagfall and coarse woody debris really begin to accumulate after 10 to 15 years. This is the classic fuels patterns that were synthesized by Hickey and his colleagues back in 2012. And this is a general pattern that I think most epidemics follow with nuances based on location. In our particular sites, the fine fuels, the litter, the duff, didn't really seem to respond quite like in some other stands that are either higher density or contain spruce and fir. So we didn't really see this significant bump in the 5 to 10-year-old stands that typically is reported. In addition, our 1,000-hour and 100-hour fuels began to taper off after snagfall and didn't continue to accumulate over decades. So we found sort of a what we might say is um, the 1,000-hour fuels really ceased accumulating very rapidly after snagfall, and our 1 hour fuels and litter changed very little. And the probably one of the key differences between our this particular forest type and other forest types that have been studied with mountain pine beetle is there's no succession to spruce and fir in this forest type. So you have this really nuanced sort of spin on the typical fire regime and fuels regime that would result from mountain pine beetle activity where you might get spruce and fir moving into the stand and where you had spruce and fir in the understory. So this sums up my portion of the presentation. Will be entertaining questions at the end. And I'd like to turn the microphone over to Michelle now.
Hi, good morning. I'm going to transition now into talking about the work we did on the Pole Creek fire, which burned through some old mountain pine beetle killed lodgepole pine stands over on the Deschutes National Forest. This is our research team. I worked on this with Travis Woolley and Stephen Fitzgerald, and our funding came from Forest Health Protection Evaluation Monitoring Program. We had a lot of help from the Deschutes National Forest Sisters Ranger District, some colleagues over at University of Idaho, as well as at WETAC. So zooming out for a moment from our specific interaction that we've been talking about this morning, I like to introduce this concept of interacting disturbances. And this is when two or more disturbance events co-occur in space and in rapid succession in time. So often we say that disturbances interact when the change to the ecosystem made by the first disturbance, those effects are still apparent by the time the next disturbance occurs. And disturbances can act in a couple of different ways. The first is that the severity of the first disturbance may influence either the severity, the extent, or the probability of occurrence of the second disturbance, and the literature has often referred to this as a linked disturbance. And the second way that disturbances can interact is through a compound disturbance. So interacting disturbances have compound effects if the effects of combined disturbances aren't additive. So therefore they can't be estimated by looking at each individual disturbance on the landscape and must be investigated where they overlap. And this is quite important to understand because compound disturbances often have effects on things like ecosystem resilience. So Dave has already given quite a lot of detail regarding mountain pine beetle, or MPB as you'll see it referred to. Um, I just want to reiterate that although outbreaks often occur over large landscapes, as you can see in this photo, there are quite a few green trees left over here. And this is really why people are so concerned about the fire issue. Uh, we really want to know what happens if there's a fire here. The conventional idea has been that all dead material will ignite more easily, leading to bigger fires, more fires in areas like these. But is that really what happens? So there have been quite a few studies that have examined this relationship, but many of them have used fire behavior models and fuel loadings measured in post-mountain pine beetle stands. And we know that these models have limitations, particularly in heavily disturbed stands like these, and there really have not been very many studies that have looked at fire behavior or post-fire effects to compare with the findings of these fire behavior models. So we had an opportunity on the Pole Creek fire, which burned during the fall of 2012 on the Deschutes National Forest in Central Oregon. This fire burned about 6 miles outside the town of Sisters over an area of a little over 26,000 acres. And the west side of the fire, kind of where you see it in the wilderness area in the map, uh, it, that area was largely made up of old lodgepole pine forest, which had experienced a mountain pine beetle epidemic between 8 and 15 years prior to the fire. And as Dave mentioned earlier, these fuels complexes are very dynamic through time. This panel on the bottom left shows the sort of progression from a green stage tree all the way through that TSP4 that he had mentioned previously. And I wanted to point out that our stands were in this sort of late gray, early old stage. And here's some more pictures of what these stands would have looked like. Quite a few standing stags are still present, but there's starting to be quite a pulse of coarse woody debris to the ground. Not much left over in the overstory canopy, and some stands had a lot of regeneration already, some did not. There's a lot of variability in this phase, but these are some um, photo representations of what it would have looked like before the fire. So we wanted to know first, how does previous mountain pine beetle severity influence both surface and crown fire severity? How does mountain pine beetle severity influence the total mortality from both disturbances combined, and how much remains alive on site following fire, or cumulative disturbance severity? And what was the dominant fire type in this study area, and how did it vary with previous beetle mortality? So just to go over what we thought would happen, um, we hypothesized that at higher levels of mountain pine beetle severity, we would see higher levels of surface fire severity um, due to the higher fuel loads on the surface in this time since beetle. And then we thought that the reverse would be true for crown fire severity. Higher levels of mountain pine beetle severity, we would see lower levels of crown fire severity because we would have fewer residual crown fuels following that higher beetle epidemic. Uh, we hypothesized no net effect on cumulative disturbance severity, and that these disturbances will sort of balance out in terms of total mortality or total surviving following both disturbances, leading to very similar conditions in that respect. And then finally, following this hypothetical trend of mountain pine beetle influence on fire behavior from the Hickey et al. Paper in 2012 that Dave had mentioned earlier, we thought we would see mostly torching and surface fire as the dominant fire types. So you can see between these two blue lines on the graph, that's the window of time that our stands were in. So torching and surface fire would have been very prevalent, and we hypothesized that we would see almost no active crown fire. So this is our study area. You can see that this is the fire perimeter located in Central Oregon. We established 52 plots, which each were represented by a triangle on this map, and we stratified plot establishment by both mountain pine beetle and fire severity. And the coloring of the map is fire severity, with the darker colors representing higher severity. Mountain pine beetle severity was determined using the aerial detection survey data, which Dave described earlier, while fire severity was determined using difference normalized burn ratio values. And I should also point out that we only looked at epidemic levels of mountain pine beetle in this study, and we excluded endemic levels of activity. So these are the photographic examples of our different burn severity categories. On the top left is an unburned plot within the fire perimeter. Below that is low severity. The top right shows moderate severity stand, and then the bottom right shows high severity. So our sampling really ranged from no change at all to sites that had no live vegetation anywhere as far as I could see. So this is our field plot in the center here. We collected our field data in the summer of 2013, so about 1 year following the fire. In the central circular plot here, we collected stand structure and fire severity data on all trees and snags, and we assigned snags all a cause of death, either mountain pine beetle or fire or something else. You can see these photos along the bottom are field technicians looking for mountain pine beetle galleries, which was how we assigned the cause of death. Um, we measured regeneration, ground cover, and soil char depth in these smaller subplots, and we tallied ground char as well as downwood along grounds transects. Um, just to briefly touch on the analysis, we used linear models to assess the effect of mountain pine beetle severity on both fire and cumulative disturbance severity, adjusting the analysis as necessary. This table shows the variables that we used for each attribute, as well as the units and analysis that we ultimately went with. Um, we used basal area killed by mountain pine beetle to describe mountain pine beetle severity. So if I say mountain pine beetle severity, that's what I mean. And then we used 6 different variables to describe fire severity, as well as 4 different variables for cumulative disturbance severity. And then in each of our models, we also accounted for fire weather using a variable called burning condition, which had 2 levels, either moderate or extreme, just to kind of separate those big fire days from the other fire days. Although we were mostly interested in the mountain pine beetle effect on fire severity, previous work in Yellowstone indicated that this type of variable is pretty important in driving that relationship, so we decided to include it. And then just to talk about the fire type analysis a little bit, this is something that we did using post-fire severity metrics, and it's a little bit difficult to assess fire type using post-fire severity metrics, but our key question here was sort of to get at whether active crown fire really occurred during this stage following mountain pine beetle or not, whether it was quite as uncommon as was previously hypothesized. So we chose a fairly conservative definition of active crown fire so that we were hopefully not overestimating its presence. Classified a plot as active crown fire if there was 100% overstory mortality, over 95% dominant canopy consumption, average bull char height to canopy height ratios exceeding 0.95, and we looked at plot photos and aerial images to kind of make sure that these conditions looked pretty similar for a distance surrounding the tree plot, just to make sure that it wasn't a whole plot just torching. And then we classified torching and surface fire accordingly. Uh, so just getting into some of the results, this is our analysis of mountain pine beetle and fire severity. There's a lot going on this slide, but I'll try to describe everything. The x-axes show that basal area killed by mountain pine beetle in meters squared per hectare. Uh, that's our mountain pine beetle severity metric. Our black lines indicate the relationship between mountain pine beetle and fire severity under extreme burning conditions, while the gray lines indicate the relationship under moderate burning conditions, and each dot here represents a single plot. On the left, we have the measures of crown fire severity that we used. So on top, the proportion of canopy consumed by fire, and then average bull char height on the bottom. In the middle are the metrics which integrate fire severity in multiple strata, basal area killed by fire on top, and average composite burn index on bottom. And then on the right are surface fire severity metrics, proportion of ground charred, and soil char depth. So each line with an asterisk indicates a statistically significant relationship, and the other lines show estimated relationships that aren't statistically different from 0 or a flat line. So there's quite a bit going on, but as you can see, each of these fire severity metrics in all the strata have a negative relationship with mountain pine beetle severity, but only under extreme burning conditions. And to me, this is kind of counterintuitive because we often think of extreme fire weather as having the ability to override other factors which influence fire. However, I sort of interpret this to mean that fire severity is driven by extreme fire weather at these low levels of mountain pine beetle severity. So when there are more canopy fuels potentially available. And then at the higher levels of mountain pine beetle severity, stands become more fuel limited, don't have that residual canopy left, and can't really support those high severity fires, even in spite of the extreme fire weather. And then under moderate burning conditions, it just seemed like there was more variability overall. So moving on to the mountain pine beetle and cumulative disturbance severity results, x-axes and line colors are the same as in the previous slide. On the top left shows the graph of post-fire live basal area, so what was left over following both disturbances. And then the top right shows cumulative basal area mortality, or total basal area killed by both the mountain pine beetle and fire. On the bottom are logistic regressions of probability of post-fire tree survival and regeneration presence, using presence-absence data from each site. So we use these to address the question of whether these disturbances were influencing the presence of a seed source on the site. And here we see that the only statistically significant relationship is a positive relationship between the mountain pine beetle severity and cumulative basal area mortality up in the top right, and that's under moderate burning conditions only. So I interpret this to mean that this is a function of total mortality being driven to a greater extent by fire under extreme conditions and more by mountain pine beetle under moderate conditions. And overall, it just seems like there really isn't much of a relationship between that mountain pine beetle severity and cumulative disturbance effects. So moving on to our investigation of fire type, here's the graph of what we expected to see on the left from the Hickey et al. Paper. Again, high levels of torching and surface fire with very little active crown fire. And then on the right is the graph of what we found. Basal area killed by mountain pine beetle again on the x-axis, and then fire type on the y-axis. And a couple of things are notable here. First is that torching and surface fire were both very prevalent. They're the most common fire types in this fire, and that was what we predicted. And we saw that at all levels of mountain pine beetle severity, those fire types occurred. However, active crown fire was in fact present in the study area, contrary to that original hypothetical trend that we were looking at. It's interesting to note that these plots mostly fell on the lower end of mountain pine beetle severity, and if we were going to see active crown fire, I think that is where we would have expected to see them, where that residual crown was more present. So just to get into a few of the limitations of this work, I wanted to point out that this is one fire, and we were looking at one stage following the mountain pine beetle. Ideally, to get at this question, we would really like to look at multiple fires across all of those stages that Dave mentioned in his portion of the talk to really understand what's happening here. So there's a lot of room to collect more on this issue. We didn't have pre-fire fuel values for surface fuels or canopy bulk density or canopy base height, which are all characteristics that we know have the ability to influence fire behavior, fire severity. And so if there are opportunities for experimental burning, under collecting that data beforehand would really inform this relationship. And of course, we all know that fuels are not the only drivers of fire behavior or fire severity. We attempted to account for fire weather, but the variable we used was pretty coarse, so just a moderate or extreme burning condition. And we don't really know how those individual components of fire weather, wind speed, relative humidity, max temperature, we don't know how these were all contributing to the interaction. So um, getting a more fine-tuned understanding of fire weather would help to understand this interaction. And also, we didn't account for topography in this study, which could have certainly been playing a role. And finally, I can't really talk about disturbance interactions without pointing out that these two, the fire and mountain pine beetle, are not the only things going on in this system. Dave talked quite a bit about dwarf mistletoe. We also have a lot of western gall rust. These are two very common pathogens in these types of forests. And we really don't know what the role is that these two pathogens are playing in this interaction between fuels and mountain pine beetle and fire. So to wrap things up, we found that fire and mountain pine beetle are linked disturbances in this system. So the severity of mountain pine beetle epidemic influences subsequent fire severity. Our hypothesis regarding crown fire severity was supported, so fewer crown fuels in the canopy did lead to lower fire severity. However, our hypothesis regarding surface fire severity was not supported. That also had a negative relationship, which was the opposite of what we expected to find. One thought I had about this is that perhaps that pre-fire surface fuel data that we didn't have could have played a role if we knew what was there before. If we'd been able to quantify the understory mortality or downwoody fuel consumption, this relationship could have been different. Cumulative disturbance severity did not show a strong or consistent trend with mountain pine beetle severity. This indicates that at this point we really have no evidence for compounding disturbance effects altering stand development patterns 1 year following the fire. Obviously, 1 year is not, we can't really get at these questions using just that 1 year of data, so long-term monitoring is needed to really understand ecosystem response over time. Torching and surface fire were the dominant fire types in the study area, as we expected, but there was a significant component of active crown fire that burned through these stands. It was far more prevalent than previously hypothesized during this stage of post-mountain pine beetle forest. So on the one hand, the higher mountain pine beetle severity decreases fire severity, but on the other hand, we do still see that active crown fire can occur in these stands. And these findings seem to be a bit at odds with one another when I was thinking about it at first. But I think that the biggest take home from this work is that mountain pine beetle severity is a huge component of this interaction. Often when we talk about mountain pine beetle activity, it's sort of simply separated into endemic and epidemic phases. But this work highlights the importance of understanding that epidemic severity and that not all stands, even within a given post-mountain pine beetle stage, are equal. So those variable levels of dead fuels and remaining live vegetation are extremely important to understanding this relationship, and they drive the fire type and they drive fire severity. So they should really be considered in future research surrounding this interaction. And with that, I'll just acknowledge some folks and I think we'll open it up for questions.
Great. Thank you so much, David and Michelle. We do actually have some questions already that have been asked earlier on, one by Susan, and let's see if I can scroll up. I don't know if you guys can see that, but Susan Jane Brown says, I'm surprised that mistletoe trees are surviving more often than not after the beetles come in. Is this accurate? If so, to what do you attribute resistance, if there is any?
Hi, yeah, this is Dave. Thanks, Susan. Yeah, so we were really amazed by that because a lot of people theorized that the mountain pine beetles moving through the west would be helping to eradicate dwarf mistletoes. But what we think is going on here is that dwarf mistletoe infected trees are not that attractive to bark beetles. There may be some association with phloem thickness, but the infected trees tend to be more in the intermediate and suppressed size classes, and their development is restricted even in some of these codominant trees. So what we're thinking is that the beetles are moving through these stands and they're taking out the most healthy trees with the thickest phloem, and it's leaving behind the heavily infected dwarf mistletoe trees as well as the intermediates and suppressed, because the beetles move into those and their fecundity is reduced. And we don't have direct evidence for that in lodgepole pine, but there's some evidence out of Alberta that this might be true in jack pine. Um, yeah, it's real, and we think the mountain pine beetle may be exacerbating dwarf mistletoe on the landscape in this type.
Okay, and then Doug had a comment. So beetles are not a problem, but a solution. They're providing ecosystem services for free. Um, so
That's a
I
good one, Doug. Well, I guess the bottom line is these are native species functioning in native ecosystems which have undergone these outbreaks. We think in this particular type that the beetles essentially never go away and they sort of come back in waves every 30 or so years. And I think a lot of the futuring that's going on with the ecologists in the region, the U.S. Forest Service ecologists and the forest health protection folks are indicating that the beetles just come back in waves as the trees come back in susceptibility. So this is something that's been going on for millennia, we believe. And um, so, yeah, I guess they are doing some services for free.
Okay, it looks like we have a question
Carrie?
from, yeah, yep.
No, go ahead.
Oh,
Excuse me.
okay. I was just going to say, it looks like another question came in from Jason, and he says, any lessons from the study for managing both forest health and natural regeneration in Eastern Oregon?
Well, one thing I would like to say is that I think this is really unique to the lodgepole pine climax type. So we don't want to directly relate this study to the non-climax lodgepole pine type. So I guess the way I would answer this question is I'm referring strictly to that area of the map where lodgepole pine was the climax forest type. And I think there's going back to this as a natural thing, I think from what Michelle has said about resiliency and from what we can see in terms of the forest type, that this is a natural cycle in this type, this interaction between the beetle and the fire and the other disturbance agents such as dwarf mistletoe and Western gall rust. So I think from one sense, it's, depending on your perspective of forest health, it's the native ecosystem going through its natural regimes. I think when you apply forest health to a managed forest or a forest where you're trying to produce timber, and then I think the implications are a little different. Um, I think obviously if you're doing active stand management and your primary concern is trees for lumber, you definitely want to, I think the standard approach is what everybody has always done is, try to salvage. And when a beetle outbreak occurs, you need to salvage within 2 to 3 years. And to maintain a healthy forest from that perspective, it would be a salvage operation or some kind of intensive management. Typically in this type, it would probably also be, might not necessarily be selective harvesting. You would actually, be treating stands. But again, I want to go back to the idea that in terms of the natural system, it's a cycle that just seems to go, come in waves, and I don't think there's anything unusual about what we're seeing in the lodgepole pine type. Hopefully that answered your question, Jason.
Great. It looks like Jim Walz is typing a question, and while we're waiting for his question to come in, I just want to remind you that I have recorded this webinar. I'm going to put it up on our website under the archived webinar section, so feel free to, send this out to your colleagues who couldn't make it today. And also, this was part of a series. The first two webinars that we had earlier in the month are also posted there, so go ahead and take a look at that. Okay, question from Jim Walls. While mountain pine beetle outbreaks are a natural system, would the size of the outbreak been different without fire suppression?
Hi, Jim. Yeah, so in this lodgepole pine type, I'm not sure that it would have been. I'm not sure how fire suppression has really influenced these systems. I think, we kind of consider them sort of similar to the mixed conifer with these fire return intervals. And so I personally don't think this type has been seriously influenced by fire suppression. Uh, I think in ponderosa pine and other systems it might be very different. But I don't know, Michelle, do you? Yeah, she's doesn't think
I,
that. Okay, here I'm gonna give her the. Oh no, no. Okay. Anyway, yeah, we're under the impression that fire suppression hasn't played a huge influence on this forest type. Hopefully, it looks like there's some people in the audience who could also answer that question. It looks like Travis Willie is typing. Travis is was extremely key to both of these studies, and um, well, we'll see what he has to say.
So sorry to keep popping in here, but while Travis is typing, I want to thank everybody. I know it's Monday morning, and especially after the AFE conference last week and the holiday, the week coming up here, Thanksgiving. I really appreciate your time, and also, Dave and Michelle's time to give this presentation today. So thank you to the speakers, and thank you to the audience for joining us. And it looks like Travis has posted his uh, response maybe on a landscape scale in terms of the amount of the landscape susceptible to beetle at any given time. Without fire suppression, there may have been more heterogeneity in age class.
Right.
I
Yeah.
have that.
Just a,
Just to jump in on this heterogeneity issue and to get back a little bit to this management question, um, our Pole Creek work to me really indicates that, and I forget who mentioned the ecosystem services, Doug mentioned the ecosystem services aspect. It really does seem like we saw at these higher levels of mortality that perhaps some of these stands were acting as fire breaks, or at least in terms of the really high severity fire, the active crown fire, maybe didn't happen in some of these stands that had been previously heavily killed by mountain pine beetle. And so it it does seem that the beetle is creating some heterogeneity, and perhaps that fire suppression did play a role at some point, but we do see that the heterogeneity is there.
Okay, do we have any other questions for Dave or Michelle? If you do, let's get those in the next couple of minutes. If not, um, again, I want to thank the audience, and I want to especially thank Dave and Michelle for giving us this presentation. You've got a really interesting thing going on here.
yeah, though the we haven't published this work yet, but we have several papers in review and in revision. So hopefully the data and the papers on this will be coming out soon.
Fantastic. Well, I don't see anybody else typing, so we are close to the close of this webinar, so we'll go ahead and make that official. And happy Thanksgiving, everybody.
Okay, thank you.
Thank you.